Thank you for inviting me to here. I am Hiroki Kegami. Now I'm working on IOP, Chinese Academy of Science, at Philo, Beijing. And I joined IOP about 6 months before. So I came China about half a year before and start to work at IOP. And today I will talk about the symmetry breaking and topology in Superfluid 3. And actually, this work was done at Riken, Japan. Yeah. Okay. First, I want to show our collaborators. These experiments were done in a low temperature physics laboratory at Riken, led by Kibitoshi Kono. He already retired at Riken, and now he is working at Taiwan, Jiangsu University of Taiwan. And this experiment was done with a student, Takahiro Matsumoto. And we are also collaborating with some theorists, the Dr. Tsumi. Now he is at Kansei Gakuin University. And I always ask him to interpret our experimental data. And we also collaborate with Super Chun. He is at Seoul, and he gave us a lot of theoretical input, and we are collaborating with Jim Soros and Alexei at Northwestern University for a long time in the study of superfluid helium 3. Yeah, this is my outline today. I want to briefly show what is superfluid helium 3, and especially I want to emphasize what is the p-Cooper pairing. And then I want to show our two experimental study. First is the first demonstration of time reversal symmetry breaking in superfluid helium 3A phase, and another is direct detection of my radar surface state in superfluid helium 3B phase. Okay. Yeah. Okay. First, I want to start from the beginning of the helium 3. Yeah, helium 3 is a fermion because it is composed, helium 3 atom is composed of 3 fermi particles, and its nuclear spin has spin is 1/2. So the helium 3 atom is a fermion with a spin half. So its behavior is actually like electron, but helium 3 does not have a charge. So it's charge neutral system. And when we cool helium 3 at low temperature, the helium 3 shows the liquefaction. So it phase transition from gas phase to the liquid phase at about 3 Kelvin. And below 3 Kelvin, it remains a liquid state down to 0 temperature. And it never solidifies, it never freezes, even at 0 temperature. This is because helium 3 atom has a large quantum fluctuation because atomic mass of helium 3 is small. So the helium 3 has a large kinetic quantum motion, and so it is difficult to solidify of the liquid helium 3. And below about 1 Kelvin, the liquid helium 3 shows the fermi degeneracy. And below 1 Kelvin, property of helium 3 is well described by Fermi liquid theory. And actually, historically, helium 3, liquid helium 3 played a very important role to establish the Fermi liquid theory by Landau. And going further lower temperature, it shows the phase transition to the superfluid state. And in the superfluid state, there are multiple superfluid phases. This is a phase diagram at the magnetic field. And the magnetic field, we have A phase and B phase. And in magnetic field, there's another phase. So there are 3 superfluid phases identified so far. So the helium 3 has multiple superfluid phases. And another important aspect of the liquid helium 3 is that our system, liquid helium-3, is very clean system. We call it ultra clean system, and impurity is actually very, very low. Impurity level is actually very low, very low. This is the estimated number, and actually there is no impurity in our system. So this means that if we do experiment, then we can get a very clear experimental result, clear-cut experimental result. And this is very important to compare to the theory. So the very clear experiment, because we can get very clear experiment, we can compare with theory without any ambiguity. So this is a very important factor for, especially for the experimentalist. Okay, and the main topic today is superfluid, about the superfluid here, and it occurs about 1 millikelvin. And in this superfluid phase, we have multiple superfluid phases, and this means that Cooper pair is not S-wave. It's Cooper pair has some internal structure, and actually it is known that superfluidity of helium-3 occurs due to the P-wave pairing. And P-wave means that Cooper pair has orbital angular momentum 1. So the Cooper pair rotate each other with angular momentum 1. And each Cooper pair has spin, so the spin 1. It means that the spin is polarized in the same direction. And in this case, there's a degree of freedom associated with the orientation of the angular momentum and spin, which means that, for example, the component of L, the component of the angular momentum can have minus 101. Spin can also have minus 101. So there are 3 degrees of freedom for the orbital angular momentum and spin. This means that each Cooper pair has 3 by 3 by 2 degree of freedom. This 3 comes from the orbital, and this 3 comes from the spin, and 2 comes from the amplitude and the phase. So totally 80 degree of freedom, and this large degree of freedom should be compared to the S-wave, and in S-wave, the no orbital angular momentum and no spin. This means that only 2 degree of freedom associated with amplitude and phase. And this large degree, so the P-wave Cooper pair has large degree of freedom, and this large degree of freedom gives rise to the various quantum effect, various exotic quantum effect. So the physics of the superfluid helium-3 is very rich, and behind of this rich physics, the symmetry, breaking, and topology play important role. This is a main message of today's my talk. Yeah, and actually symmetry breaking in this system is very complicated, so I don't go detail of this one. And but I just want to today I just want to tell only 2 things. One is time reversal symmetry breaking in this phase, and another is the topological property in this phase, D phase. And this phase diagram is this is a phase diagram at 0 pressure, and at 0 pressure we have 2 phases, A phase and B phase. A phase is stable in a magnetic field, but the B phase becomes stable at the low magnetic field and low temperature region. And for each phases, today I want to tell about the symmetry breaking and topology. Okay. So the first I move to our experimental result. First I want to I want to tell about the experiment in this phase, A phase. Now this phase breaks time reversal symmetry, and recently it is considered as a wild phenomenon. And I want to tell more about the time reversal symmetry breaking in A phase. In A phase, the Cooper pair, Cooper pair. In A phase, all Cooper pair rotate in the same direction, like this. And this means that the angular momentum of Cooper pair align in a particular direction. In this case, angular momentum orient this direction. So this means that angular momentum is oriented in the particular direction. And in this case, the orbital motion breaks time reversal symmetry, because if you reverse direction of time, the Cooper pair rotate in the opposite direction, and this state is different from this original state. And so the direction of the angular momentum is described by vector L, and its order parameter is given by this. Kx plus iky indicates the orbital motion of the Cooper pair. And this state has an energy gap like this. At the north and the south pole, there's a north. And along this direction corresponds to the direction of the vector L. And we call the direction of L as a chirality, because the Cooper pair shows a chiral motion. And so far, in helium-3, superfluid helium-3 was discovered in 1971, and for a long time, for about 40 years, there was many experiments was done, and all of the experimental results were consistent with time reversal symmetry breaking, but there is no direct experiment. There's no direct demonstration of time reversal symmetry breaking in this phase so far, and we have demonstrated time reversal symmetry for the first time, as I will explain before. But before going to our experimental result, I want to put some comments on the time reversal symmetry breaking in superconducting system. So far, there are some superconductors which might break time reversal symmetry, but all of the experiment system, in all of these materials, the situation is still controversial. There's some discrepancy between the different experiments. Yeah, and especially strong single lucinet, which is long believed to break time reversal symmetry. But rather recently, several years before, this system, this time reversal symmetry breaking in this system become very controversial by the some NMR experiments. So in any superconductor, there's no, in my opinion, there's no well-defined time reversal symmetry breaking system. And okay, and I return to my system, superfluid helium-3. Before our experiment, there is no direct demonstration of time reversal symmetry breaking, and we tried to demonstrate the time reversal symmetry breaking in this system. And what we do is rather unique, and we use electron produced inside of the liquid helium. When we make the electron inside the liquid helium, the electron forms a small open cavity with the size of the nanometer, like this. We call it this structure as electron bubble, and its size is much smaller than the coherence length, which is about 80 nanometer. So this electron bubble can be taken as a microscopic probe to study the property of superfluid helium-3. And we use this transport of this electron bubble to study the property of superfluid helium-3. And to observe the time reversal symmetry breaking, we measure transport of this one, and so in the helium-3 Fs, which breaks time reversal symmetry, this electron, there is theoretical work that this electron motion of this electron bubble show the anomalous Hall effect. This theory was this effect was predicted quite a long time ago, but there's no experiment. So in this theory, this theory says that the electron bubble moves inside the liquid, then it shows the anomalous Hall effect, and the vector L plays a kind of effective magnetic field, and this anomalous Hall effect arises from the skew scattering of quasar particle, and at finite temperature there are thermally excited quasar particle, and which scatter the electron bubble, and the scattering becomes very unusual in the superfluid HEM3. This picture shows the scattering amplitude of this system. Quasar electron bubble is located here. Quasar particle is coming here, and scattered by the electron bubble. After scattering electron bubble, after scattering quasar particle scattered in this direction. The scattering amplitude is actually asymmetric with this plane, and more scattering amplitude in this direction. This means that the quasar particle is more scattered in this direction, which means that the electron bubble recorded in this direction. And this asymmetric scattering results in the anomalous Hall effect in this system. Yeah.
So you apply magnetic field to realize this?
Yes, yes. Fs, yes.
So then the time reversal field is not going to
broken by magnetic field, but it's a spin part. Spin part of the spin part is time reversal symmetry is spin part is broken by magnetic field, but the orbital part is not, because the Cooper pair itself has no charge, so it does not couple to the magnetic field. Yes, 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 yes.
You have two wire nodes, right? So you have two wire nodes.
Here, and here. Yeah, it's both. Yes, yes, yes.
And why there's weird structure of
this interference. Interference. This is the size of the electron bubble is order of nanometer, and Fermi wave length is 3 angstrom or something like that, roughly 10 times larger. And this interference pattern corresponds to the how to say ratio of this number and this number. So the KF of Helm3. Helm3.
This is about
Fs.
You have no
Fermi surface. Yeah. Fermi surface. Fermi surface, and there's an energy gap on the Fermi surface. It's okay. In a bulk. This effect is in a bulk. Okay. Okay, and in EFS, the theory predict the anomalous Hall effect, and in our experiment we measure this anomalous Hall effect, and to measure anomalous Hall effect, we utilize free surface. We can trap an electron bubble just below the surface, which is typically several tens nanometer below the surface, and measure transport along this way, along the surface. And we can make a uniform orientation of L at the surface, because the Cooper pair rotating in this direction is broken by the surface scattering. So the Cooper pair rotating like this, L vector perpendicular to the surface is more preferred. So the uniform alignment of a vector is naturally formed in this system. And if we measure transport of electron bubble along the surface, the velocity of electron bubble and vector L are perpendicular. So we can expect the abnormal Hall effect in this setup. And the actual experimental setup is like this, because we cannot put the lead line on the electron bubble system. We use the capacitive coupling method to measure transport. We put 3 electrodes like this, input right and left electrode, and we apply the AC voltage on one electrode, which induces a current of electron bubble along the surface. And the induced current is detected by left and right electrode. And if anomalous Hall effect occurs, then we should observe the different current for both left and right electrode. So the dye should not be zero. And depending on the direction of the vector L, the direction of the current is different, so that we can distinguish which one is realized from the sign of the delta I. This is basic experimental scheme, and this experimental setup was mounted on our nuclear demagnetization refrigerator, which I made, and this reached temperature about 40 microkelvin, and we can keep very low temperature for a long time. And we put our setup here in the experimental space and measure the transport. Okay, and this is our experimental result. This is a difference of current measured by left and right electrode, and this is temperature. In normal state, there is no delta I, but in the periodic transition temperature, we observe the finite magnitude of delta I. So this means that the electron bubble show the anomalous Hall effect in our system. And what is interesting in this experiment is that in the first cooling, we observe this behavior and warm up to the normal state and cool it again. We sometimes observe the opposite sign of the current like this. This means that for green one, run one, the vector L is pointing downward and current flow like this, and in run 2, the vector L is pointing upward and current flow like this. And what is interesting is that we cannot know which one, run 1 or run 2, will appear in advance. We cannot know in advance, and we cannot control which one will appear. So we only know that after cooling, which we can know which one is actually realized. So this is a spontaneous process. So the helium-3, superfluid helium-3 select either a vector pointing down or pointing up. So this is a spontaneous symmetry breaking process, and the observation of the anomalous Hall effect is a direct demonstration of time reversal symmetry breaking. And to further check that this anomalous Hall effect arises from the time reversal symmetry breaking, we did the same experiment at in the helium-3 B phase. This is the time reversal invariant state, and at this magnetic field, at the beginning it is A phase, and so it follow the same line, but in the B phase it will suddenly drop to the zero value. So this means that our observed transverse current is arising from the time reversal symmetry breaking. Okay. And actually, this this kind of signal is like resonance behavior, and we measure this transverse current in the frequency domain, and it shows the resonance-like behavior. And we analyze this data by using numerical simulation. I skip detail and calculated response, and we can fit the resonance line in frequency domain, and from the fitting we can extract the magnitude of whole angle between the electric field and velocity as a function of temperature. And whole angle increases with lowering temperature. And this experiment was done in 2013. After our experiment, the theoretical group at Northwestern University reproduced our experimental result quantitatively. And in this theory, there's no fitting parameter. They use only the known parameter for the superfluid chemistry. There's no fitting parameter, and they can reproduce our experimental data quantitatively. Okay, and yeah, and helium-3. So in our experiment, we show that helium-3 breaks time reversal symmetry, and this time reversal symmetry breaking is the very important factor to be the helium-3 as a topological state. And theoretically, helium-3 phase is known as wild superfluid. It has a wild node at North Pole and South Pole, and here there's a singularity which we call hedgehog. And around here, the quasar particle is described by wild Hamiltonian. And because in this wild system, in wild system, there's a edge current, or in this case, surface current, chiral surface current, like this. And it has surface current has a linear dispersion, and its direction is opposite for the opposite surface. And such wild feature of the wild fermion is actually working in our experiment. This is a theoretical calculation by Northwestern group, and from the calculation, the around the electron bubble, there's a bound state. It's a chiral bound state, and on the surface, the chiral current flow like this, and it is it has a linear spectrum, but around the electron bubble, the chiral bound state is also formed, and because it's a small size, because electron bubble is kind of a small surface, so the energy level is discretized, so it has discrete chiral bound state around the electron bubble, and such chiral bound state shows the causes skew scattering of the quasar particle. In our experiment, we are observing the skew scattering caused by the caused by a chiral bound state around the electron bubble. Okay, so so far we have studied, we show the experimental result only for the single domain, but in some cases, in some cooling, we observe the formation of multiple chiral domain, and in that case, this blue signal is noisy and also shows jump here and here, and also here, and this jump is actually caused by earthquake. In Japan, we have a lot of earthquake here, so the earthquake causes the jump in the signal. This is actually not noise, but actually this jump is caused by the motion of domain world. if we have a domain all like this, and we give a mechanical shock in the cluster, this domain will move, because the mechanical shock actually induces current inside, and this current induces the motion of domain wall. So the domain will move, and this jump of signal corresponds to the motion of the domain wall. And the domain wall recently visualized by using MRI by Kyoto group. This is an example taken by picture of the MRI down at the Sasaki group at Kyoto University, and the domain wall will form like this. And yeah, here you can see the line, and this line corresponds to the domain wall, and this is a structure of colored domain wall calculated from this experimental signal. Okay, but in the this is not our experiment, but they applied the gradient of magnetic field, and they do the pulse NMR, and because of the gradient, the different position has a different resonance frequency. And I think sorry, I have not known detail about it. Yeah. Probably they measure the after pulse they measure the free induction decay, and analyze the frequency. They can see the different position. Okay. Moment. Actually, it's very usually stable because it is pinned at the edge of the sample cell. For example, in our experiment, it's rather stable, not stable, but it can move. Here, signal is fluctuating. This means that the domain wall is probably moving, but it does not move so largely because they are pinning. But it at the center of around the center, it can move. But the mechanical shock, by the mechanical shock pinning side, pinned domain wall is can move by the mechanical shock. Yeah, we are in this case experiment. We observe only at the surface, so we don't know how it is inside. Yeah, in our experiment we trap at the bubble just 10 nanometer below the surface, and we cannot go deep. Yeah, I will explain later. Yeah, and in this experiment, they for example, to take this one picture, it takes about I don't know exactly several hours or 10 hours. It takes a long time, and during that time, the domain will seem to be very stable. Okay. All right. Just a moment. Okay. And in the case of a single domain, signal is very stable. Actually, this red arrow corresponds to the earthquake mechanical shock, but the signal is very stable here. And this is because in the case of the single domain like this, to make the chiral domain, we have to destroy the superfluid here locally, and then make the opposite chirality to make a chiral domain. And it requires a lot of energy, and actually such a process does not happen in real system. So the signal is very stable, and this stability is due to the topological stability, because the opposite chirality has an opposite topological number, and we cannot go to the opposite chirality just by the continuous transformation of the order parameter. So this is due to the topological stability. Okay. So I want to go to my second topic. Second topic is direct detection of Majorana surface state in helium 3P phase. Next to this phase. This phase has a energy gap like this. It's an isotropic energy gap, like SF Cooper pair, but it has a spin degree of freedom. And the orientation, direction of spin has on the film surface, direction spin changes like this. So on the film surface, or the direction spin changes to pi if you go around the film surface. And this corresponds to that there is a monopole at the center of the momentum space. And this leads to this kind of spin structure. And because of this spin structure, it has a topological number, and we can define topological number, and this helium 3 is known as time reversal invariant topological superfluid state. And in a topological state, there's at the surface of topological superfluid, there should appear the surface bound state. This is because of the bulk surface correspondence, and surface state is formed, and this surface state should have a different property from the bulk state. And in the case of the helium 3, this bound state is formed with a coherence length, which is about 80 nanometer. So the bound state is formed 80 nanometer from the surface. And this bound state is theoretically considered as Majorana surface, Majorana fermion. Majorana fermion is a fermion in which particle state is identical to the antiparticle, and originally proposed for the elementary particle, but recently Majorana fermion is expected to be realized in the condensed matter system. And in condensed matter, the antiparticle state is actually false, so the particle state is identical to the whole state in the Majorana fermion. And such Majorana fermion can be made in the P-wave superfluid, because the superfluid or superconductor, number of quasar particle, number of Cooper pair are fluctuating, so the particle state can be identical to the whole state, but this is not sufficient. We have to also consider the orientation of spin, and to make the Majorana fermion, we have to make the spin state the same as the particle for and whole. And only P-wave, only spin triplet state, like P-wave, such equal spin pairing state is possible. So the P-wave Cooper pairing state is the ideal system to study the Majorana fermion in condensed matter system. And my naive question is that whether Majorana fermion really exists in nature, and if it exists, what novel property Majorana fermion have. And we perform experiment to detect the Majorana fermion at the free surface. Yeah. And there are several experimental studies in other systems, in condensed matter system. such as a hybrid system of the semiconductor, nanowire, and superconductor, and vortices in topological superconductor, and some spin liquid state. And now there are several experimental results which indicate the presence of Majorana fermion in condensed matter system. And in helium-3, helium-3 is also one of the important platforms for the study of Majorana fermion. And in our experiment, this is our experimental scheme to detect Majorana fermion. In this experiment, we also use an electron bubble trapped at the surface. And we can trap electron just below the surface, and we can tune the depth from 20 to 60 nanometer. I will explain how to do it later. And this depth roughly corresponds to the depth of the Majorana fermion formed. And if we measure the transport of the electron bubble, and the electron bubble is scattered by Majorana fermion, then mobility should be affected. So if we measure the mobility just below the surface, the amplitude of the Majorana surface state is large, so the mobility is much affected. But if we measure far from the surface, mobility is not affected by the surface, Majorana surface state. So we expect that the depth dependence of the mobility in this experiment. This is our experimental setup of this experiment. Yeah, in this case, we also trap the electron bubble below the surface, and we measure transport by using Corbino electrode located above the surface. And electron bubble is trapped by applying the DC voltage on the bottom electrode, which is immersed in liquid helium, and this produces a vertical electric field like this. And so this field produces this part, a linear part, and because electron inside the liquid field repulsive force from the surface, so it gives this kind of repulsive force from the surface. So that we can make the potential well like this, and by changing this field, we can change the minimum position of this potential well. By using this method, we can control the depth of the electron bubble. And the typical range of the typical tunable range is 20 to 60 nanometer from the surface. And this is our experimental result. And this is mobility as a function of temperature. And this blue data is taken at 58 nanometer from the surface. It increases with decreasing temperature like this. And we repeat the same experiment at different depths. And this is 37, 27, 21. So the all experimental data follow on a single curve. This means that there is no depth dependence, which is an unexpected experimental result. And another thing we noticed is that this blue line is a theoretical mobility of the electron bubble in bulk, and our observed mobility at the surface is smaller than bulk mobility. This means that there's additional scattering near the surface, and actually this additional scattering arises from the Majorana surface state. This blue line, this red line is theoretical curve calculated by Dr. Tsubihi, and he calculated the mobility of electron bubble near the surface by including the influence from the Majorana surface state. So as you can see, our experimental mobility quantitatively agree with the theoretical curve. This means that our experimental mobility determined by the bulk effect plus Biolanner surface effect. And actually, this difference from the bulk to this blue and difference between blue and red correspond to the contribution from the Biolanner surface state. And at the lowest temperature, about half of the mobility is coming from the Biolanner surface state. And he also calculated the mobility at different depths, and actually the all theoretical curve fall on the same line. So his calculation shows that there is no depth dependence. And in his calculation, there is no fitting parameter. Only the parameter known in the Superfluid He is used for this calculation. Our experimental data quantitatively agree with his theoretical calculation. And this strongly suggests that in our experiment, we detect Biolanner surface state.
So, the electron bulk is theoretically very deep inside the mass.
Theoretically, it should be blue line.
Right. So the difference must depend
on the depths. I'll explain next.
Is the Biolanner surface state, does its density depend on temperature or not?
It's a somewhat excited to Biolanner surface state. So at higher temperature, more Biolanner surface state are excited.
You also mentioned that coherence length is
80 nanometer.
That must be temperature dependent?
It's temperature dependent. And 80 nanometer is the coherence length at 0 temperature.
So it must be much longer.
Much longer at high temperature. But around coherence length diverges at transition temperature, but only near the temperature, near the transition temperature, it's large. It soon become close to the 80 nanometer. And I look into his theoretical calculation in more detail. This is the depth dependence of the mobility as a function. This is mobility as a function of the depth. And his calculation shows that up to around four times of the coherence length, there is no depth dependence. And actually, this for coherence length is it's just order of the coherence length. And this mobility in this in his calculation, so our electron bubble is actually the small surface, so it also have a bound state around there, discrete bound state around there, like this. And this electron bubble approaches to the Biolanner surface state. Then this bound state and the Biolanner surface state mix and cause it gives rise to the scattering of the electron bubble. And this scattering amplitude shows this kind of behavior. Some peaks show the peak structure, and this peak structure actually correspond to the presence of the bound state around the electron bubble. And as approaching to the surface, a mixing of this bound state and Biolanner surface state becomes stronger, and this results in the decrease of scattering cross section. Which is E. This is the energy of energy of quasar particle. So this is a gap. One corresponds to gap, and this is inside of gap. So cross section, scatter cross section decreases, but as approaching to the surface, the amplitude of the Majorana surface state becomes larger, which means that density state get larger, and this increase and this increase of the density state and the decrease of scatter in cross section accidentally cancel, and it gives rise to the lack of the depth dependence of the mobility near the surface. Okay, this is my conclusion today. We show that the Superfluid 3He is an excellent platform for exploring novel phenomena arising from the symmetry breaking and topology. And the Helium-3 we discovered anomalous Hall effect of epsilon bubble, and observation of the anomalous Hall effect directly corresponds to the demonstration of the time reversal symmetry breaking. And the Helium-3b phase, we detected the Majorana surface state by mobility of epsilon bubble, and this means that our experimental result theory quantitatively agree. And this quantitative agreement means that our electron bubble is a very excellent probe to study the property of Majorana state quantitatively. And there are very important challenge to be done. First is to detect chiral Majorana state, which appears in the superfluid Helium-3 phase, and also the some topological phase transition is theoretically predicted in Helium-3 phase. And a very important challenge is to verify the surface state is actually the Majorana state. I mean that in our experiment, we just show that there's a surface bound state at the free surface, but we have not proved that it is really Majorana fermion. And proving Majorana fermion is very, very important for future work. Thank you very much.